90.04%.
That is a very specific, very precise number to kick things off with.
It is, yeah. But in our world, specificity usually signals something pretty important. Welcome to the Deep Dive, everyone. I'm your host, and I'm sitting down with our resident AI expert to do what we always do. We're going to unpack the source material and see what's actually going on under the hood.
Glad to be here. And yeah, let's talk about that 90.04%.
Right, so that number is the score achieved by a specific AI model on the MMLU benchmark. That's the Massive Multitask Language Understanding test. And the reason I'm throwing a decimal point at you right off the bat is because of who, or rather what it actually beat. Human experts.
And when we say experts, we really don't just mean the average person taking a trivia test.
Exactly. We are talking about people who study these specific fields for a living. Physics, history, medicine, law. They usually sit at about 89.8% on this massive exam. So breaking 90% isn't just a high score, it's a literal threshold being crossed.
It's the exact statistical moment the machine edges out the specialist. Which is wild to think about.
It really is. We are looking at the first model to officially outperform human experts on this benchmark. And that brings us to the subject of today's deep dive. We are tearing apart the technical report for Gemini, or as the paper calls it, a family of highly capable multimodal models.
Right. This is the comprehensive technical report directly from the Google DeepMind team. And I think tearing apart is the right phrase here because, let's be honest, there is a whole lot of marketing fluff in the AI space right now.
Oh, absolutely. Everyone claims their model is the smartest, the fastest, the best.
Exactly. So our mission today is to kind of ignore the press releases for a bit. We want to look at the actual architecture. We need to figure out if this is fundamentally different or if it's just, a bigger calculator.
Yeah, and we're going to dig into this native multimodal concept, which I'll admit sounds like total buzzword soup at first glance. But it might actually be a massive shift in how we engineer these things.
We also have to talk about the hardware. Because to get that 90% score, they had to build physical infrastructure that borders on science fiction.
Definitely. And we'll look at the family aspect too, right? Why there isn't just one monolithic model, but 3 distinct versions, including one that literally fits in your pocket. But let's start with that architecture. The report uses this phrase constantly, natively multimodal.
It's everywhere in the paper.
Right. Now, to the more cynical part of my brain, that just sounds like branding. I mean, we all know other models can see pictures. You can upload a photo to almost any major AI right now, and it can tell you what it is. So what is the actual structural difference here?
It is a really significant difference, actually. It basically comes down to how the model was raised, so to speak. Historically, if you wanted an AI to see and to talk, you took a really good language model, which is essentially a text brain, and you stitched it together with a totally separate vision model.
Kind of like a Frankenstein approach?
Roughly, yeah. You're training a visual specialist on one side and a text specialist on the other, and then you are forcing them to pass notes back and forth. The vision part looks at an image, it converts it into a text description, and then passes that text to the language model.
But in that translation, you have to lose a ton of nuance. It's like playing a game of telephone.
Exactly. Because you're forcing rich, dense visual data to be compressed into words before the actual brain even gets to think about it. Gemini is fundamentally different. It was trained jointly on image, audio, video, and text data from the very beginning.
Okay, so it didn't learn to see and then learn to speak later.
Right, it learned both simultaneously. With Gemini, a pixel is just another type of token, the exact same way a word is a token.
So it's not translating at all. It's essentially thinking in images and text at the exact same time.
Precisely. And this allows for what the researchers call cross-modal reasoning. It isn't just describing what it sees to itself. It is actually reasoning about the visual data alongside the text and audio inputs.
Okay, I think I need a concrete example for that, because cross-modal reasoning is still a bit abstract. The report had a really good one, didn't it? The one about the skier.
Yes, the handwritten physics problem. This is a classic stump the AI kind of test.
Right. So for you listening, imagine a user uploads an image. It's a messy handwritten physics problem on a piece of paper. A student has drawn a little skier on a slope and scribbled down some mathematical calculations to try and find the skier's speed at the bottom of the hill. And, spoiler alert, the student actually got the answer wrong.
Now, a standard stitched model would struggle with this for a few reasons. First, just reading messy handwriting is hard enough. But second, it has to accurately map that handwriting directly to the hand-drawn diagram. It has to know that the specific scribbled number refers to that specific angle in the drawing.
But Gemini does something really interesting in the report. It doesn't just read the text. It understands the actual physics formulation from the drawing itself.
And this is the real kicker here. It identifies exactly why the answer is wrong. It creates a diagnostic. It realized that the student used the wrong value for potential energy. They used the length of the slope instead of the vertical height.
Wow.
Yeah, the model spotted that specific conceptual error effectively because it could read the diagram and the math as one single coherent thought.
So it didn't just spit out, wrong answer, here's the right one. It said you used the wrong variable right here. It's almost debugging the student's brain.
Exactly. And then it went ahead and generated the correct solution, fully formatted in mathematical typesetting using LaTeX. It's essentially grading the paper and tutoring the student simultaneously.
That covers the visual and text integration nicely. But the native part applies to audio too, doesn't it? There was that omelet example.
Right, the cooking example. This really demonstrates the temporal aspect, meaning understanding how things change over time. In the example, a user is cooking. They upload a sequence of images of a pan with eggs in it, but they are also talking out loud to the model. They ask, verbally, does it look ready?
So the AI has to process the raw audio file, process the stream of images, and understand the real-world context of cooking an omelet all at the same time.
And it has to understand what ready even means in the context of an omelet. The model analyzes the audio signal, which it processes natively at 16 kilohertz, by the way. Here's the question. Looks at the fine-grained visual texture of the eggs in the image and responds, it's not ready because the eggs are still runny.
The eggs are still runny. That is such a distinctively human observation. A standard computer vision model might just say something like, object is pan, contents are yellow substance, confidence is 99%. But saying runny implies a physics-level understanding of texture.
It really does. And then later in the example, the user sends a new image and asks, what about now? The model actually sees the texture change. It notices the eggs are firmer, drier, and it says, it looks ready now. You can take it off the heat.
It's connecting all the dots between the sound, the sight, and the logic. That really highlights the native difference. It's not three models stacked on top of each other in a trench coat. It's one model with multiple senses.
That is a great way to put it. But as you can imagine, building that one model isn't exactly simple. It takes massive, massive resources. And that actually brings us to the family aspect of the report's title, because they didn't just build one single brain.
Right. They built three,
Right.
Ultra, Pro, and Nano. And I really appreciate this approach because in the tech world, we tend to obsess over the biggest, baddest model. But the report makes a very clear case for why one size really doesn't fit all.
It's essentially the Goldilocks strategy applied to computation. At the top end, you have Gemini Ultra, which is the heavy lifter.
The absolute genius in the data center.
Right. When we talk about that 90% MMLU score, or highly complex reasoning, or state-of-the-art coding, we are talking about Ultra. It has the most parameters. You can think of parameters as the synapses or the connections in its neural brain, but obviously that comes at a high cost. It required massive computational power just to run.
So you're definitely not running Ultra locally on your laptop.
Definitely not. For Ultra, you're sending a request to a massive Google data center, and they are spinning up serious hardware to calculate the answer for you. Then, a step down, you have Gemini Pro. This is the workhorse of the family. It's performance optimized to balance capability with cost and latency. If you're using the standard Gemini chatbot applications, what used to be called Bard, you're likely talking to Pro.
But the one that actually caught my eye as maybe the most impressive engineering feat wasn't the biggest one. It was the absolute smallest one. Gemini Nano.
Nano is fascinating because it totally breaks the industry trend of just assuming bigger is always better. Nano is specifically designed for on-device inference.
Let's define that clearly for everyone. On-device inference means it runs entirely on my phone. Like no internet connection needed at all.
Exactly. Zero data leaves your device. This is a huge deal for privacy, obviously, but also for speed and latency. You don't have to wait for a signal to bounce to a server and back.
But how on earth do you fit a large language model onto a smartphone? These things usually require terabytes of memory and massive racks of graphical processing units.
They essentially had to distill the knowledge down The report specifies that Nano actually comes in two sizes. Nano 1, which operates at 1.8 billion parameters, and Nano 2, which is 3.25 billion.
Wow.
Yeah, and for context, the biggest frontier models out there are rumored to be well over 1 trillion parameters. So compressing that core intelligence down to 1.8 billion while keeping it smart enough to be useful, like for summarizing audio recordings or suggesting text replies locally, is a massive optimization breakthrough.
It's like trying to fit the entire Library of Congress into a single backpack. You have to be very, very selective about what books you actually decide to keep.
And you have to be incredibly efficient about how you pack them in there.
Speaking of packing things efficiently, I want to geek out on the hardware for just a minute, because the report goes into some really cool detail about how they physically trained these models. They used Google's TPU's tensor processing units.
Specifically, they used the V4 and V5e generations of TPUs. These are specialized chips designed specifically to handle the dense math required for neural networks.
But the scale of it is what really got me. They were using what they call superpods, which are 4,096 chips all connected together. And there's this really honest, kind of gritty detail in the report about what actually happens when you hook up that many chips together for a long time. Things break.
Oh, yes. The silent data corruption.
SDC. It sounds like a sci-fi villain.
Hmm.
Warning, we have encountered silent data corruption.
It really is a villain for the engineers. You have to understand, when you are training a model at this massive, unprecedented scale, hardware failure isn't an if, it is absolutely a when. You have cosmic rays literally flipping bits in the memory. You have silicon naturally aging under intense heat. You have thousands of miles of cables where one might get loose. Usually when a normal computer crashes, it tells you. It freezes, or you get a blue screen of death.
Right, you know something is broken immediately, so you just restart it.
SDC is much worse. It's when a calculation goes fundamentally wrong, like the computer decides 2 + 2 = 5, but the machine doesn't tell anyone. It just keeps going. It silently corrupts the training data step by step.
So you could easily spend weeks training this multi-million-dollar model, burning incredible amounts of electricity,
Yeah.
only to find out at the very end that it's basically brain damaged because of a silent math error that happened 3 weeks ago.
Exactly. And the scary part is the report notes that these types of silent errors happen every week or two at this scale of compute.
That is genuinely terrifying from an engineering perspective.
Yes.
So how did they solve it?
They had to build an entirely new, incredibly robust immune system for the hardware. They built scanners that continuously run in the background to detect these silent errors as they happen. And crucially, they didn't rely on traditional storage checkpoints. They kept intact model replicas live in memory.
Explain how that works.
Usually, if a massive training run crashes, you have to reload everything from a checkpoint, which is essentially a giant save file on a hard drive. That takes time, a very long time. Google instead kept a hot copy of the healthy model live in the active memory of other chips on the network. So if one part of the supercomputer failed or threw a corrupted error, they could instantly switch over to the healthy copy and just keep training without skipping a beat.
It's like performing open-heart surgery while the patient is actively running a marathon.
That is a very apt analogy. It really highlights that at this elite level, AI development isn't just about writing clever code anymore. It's about managing heavy, complex industrial systems engineering.
Okay, so they built the factory, they kept the machines running despite the SDC. Now let's look at the actual product, the report card. We mentioned the 90% MMLU score earlier, but I have to ask the skeptics question here. Is that score real? Or is it just memorization? Because we've definitely seen models cheat by accidentally memorizing test questions from their training data before.
That is the big ongoing debate in the field right now. But to their credit, the report is very transparent about exactly how they got those numbers. Gemini Ultra achieves state-of-the-art or SOTA results in 30 out of the 32 benchmarks they reported. That is a pretty dominant sweep.
But for the MMLU specifically, they noted that they use something called chain-of-thought prompting with 32 samples. What does that actually mean in practice?
So standard AI testing usually looks at something called greedy sampling. That means the model takes its best guess immediately, one shot, first thought. Chain of thought is a different approach. They prompt the model to explicitly think step by step. And the 32 samples part means they actually let the model generate 32 different possible reasoning paths and answers, and then it internally evaluates and selects the best one out of that pool.
Wait, isn't that kind of moving the goalposts a bit, I mean, if I get to take the SATs and write down 32 possible answers for every question and then just submit the one I think is best, I'm probably going to score a lot higher too.
It definitely sounds like it at first, but think about how a human expert actually works. If I ask a real physicist a highly complex question, do they just blurt out the very first thing that pops into their head? No, they deliberate. They grab a piece of paper, they scratch out some notes, they check their logic, they try a few different approaches.
Ah, I see. So chain of thought is basically giving the AI a mental scratch pad.
Exactly. It's not cheating so much as it is changing the testing methodology to better match the model's actual capability to reason over time. It proves that the deep knowledge is in there, but it sometimes needs the right architectural structure to effectively extract it.
That makes sense. Let's talk about math for a second, because I feel like for a long time, large language models were amazing at writing poetry, but just terrible at basic algebra.
That is changing very rapidly. On the GSM-8K benchmark, which is essentially grade school level math word problems, Gemini hit 94.4% accuracy.
Okay, but grade school math is still grade school math if Johnny has 5 apples.
True. But then look at the math benchmark, all caps, MATH. That is competition-level mathematics. We're talking extremely difficult proofs and high-level problems. It scored 53.2% on that one.
53% sounds like an F to most people.
Right, but in this specific context, 53% is bordering on genius level. Most previous models scored in the single digits, or maybe the low 20s if they were lucky. These are problems that regularly stump human math majors. To get over 50% requires real, structural, logical deduction, not just simple pattern matching.
And what about coding capabilities? I know a lot of our listeners use these tools heavily for programming assistance.
This is where they introduced a system called AlphaCode 2. It's a specialized coding system powered directly by the Gemini models. And they didn't just test it on standard, simple coding interview questions. They threw it straight into the deep end on Code Forces.
The competitive programming platform.
Right, where the best human programmers battle it out to solve incredibly complex algorithmic puzzles under strict time limits. AlphaCode 2 actually ranked in the top 15% of all entrants.
Top 15%. That means it is literally better than 85% of the humans who are confident enough to enter a competitive coding tournament in the first place.
Correct. And to give you some scale, the previous version of AlphaCode was only in the top 50%. So the jump in capability between generations is massive. AlphaCode 2 creates a dynamic programming solution. It actively explores the search space of possible codes and then clusters them to find the most likely correct one. Again, it's that deep reasoning capability coming to play.
So definitely not just fancy autocomplete anymore. It's actual architectural problem solving.
It is, and it's doing this kind of heavy lifting across human languages too, not just code. The report specifically highlights its multilingual prowess. On the WMT23 translation benchmark, Gemini Ultra had the highest translation quality for out-of-English tasks compared to the other top models.
Out of English meaning translating from English into other foreign languages.
Yes, and crucially, it performed surprisingly well on what we call low-resource languages.
Define that term for us, if you would.
Low-resource languages are languages that simply don't have billions of web pages of text available to train an AI on. Think of languages like Tamazight or Kanuri or Quechua.
Right, if you're scraping the internet for training data,
Yeah.
you have an endless supply of English and Spanish, not so much Quechua.
Exactly. But because Gemini has such a strong foundation of general reasoning and multilingual transfer capability, it can actually pick up the structural patterns of these low-resource languages much faster with far less data. And that is a really big deal for global accessibility. It means these advanced tools aren't just going to be locked to the English-speaking world.
And real quick, touching on visual complexity, they also tested on the MMMU benchmark, right?
Yes, the massive multidiscipline multimodal understanding benchmark.
Basically college-level problems that heavily involve images.
Right, and Gemini Ultra scored 62.4% there, which outperformed the previous best model by over 5 full percentage points.
Which is a huge leap in AI benchmark terms. We've talked about logic, math, code, language, and college exams. But I want to pivot to the right brain for a second. Creativity. The report had a section on interleaved generation that I found really fun to read.
Oh, this goes directly back to that native multimodal concept we started with. Since the model speaks image and text fluently, it can seamlessly mix them.
The yarn example was the one that really stuck with me.
It's a fantastic demo of the capability. The user gives the model 2 images, one of blue yarn and one of yellow yarn. Then the user provides images of pink and green yarn and asks the model for creative ideas of what to make with them.
And a standard older AI would just write out a text list.
Right.
Like, you could make a hat, you could make a scarf.
Right. But Gemini generates text and images together, interleaved naturally in the response. It suggests making a green avocado with a pink seed, and it actually generates a picture of a crocheted avocado right there in the text. Then it suggests a green bunny with pink ears, and natively generates that image too.
And just to be totally clear on this, it's not calling up an external separate image generator like, hey, Midjourney, go make a bunny for me. It's doing it all by itself.
It is creating those images natively. It's all one continuous thought process. Think of it like this. When you are explaining a complex concept to me and you grab a napkin to sketch a quick diagram, you don't switch to a different brain. You talk and you draw simultaneously. Gemini is doing the exact same thing.
There was a more technical example of this too, using matplotlib.
Yes, for the Python coders out there, the user asked the model to rearrange some subplots of scientific functions. To successfully do that, the model had to doubly understand the Python code, but it also had to understand the actual visual layout of the graph, where the lines were intersecting, how the axes were physically labeled on the image.
It's essentially debugging the written code by looking at the visual output picture.
Precisely. It seamlessly connects the abstraction, the code, with the reality, the plotted visual.
Okay, this all sounds incredibly powerful. But with great power comes the safety section. And the report devotes a huge chunk of text to what they call post-training.
This is a critical part of the process because the raw model, the one that comes fresh out of that massive superpod training run, isn't what you or I ever interact with. That raw model is just a pure prediction engine. It just predicts the next word or the next pixel based on its training. It has absolutely zero moral compass.
So how do they actually give it one?
Primarily through SFT, which is supervised fine-tuning, and RLHF, which stands for reinforcement learning from human feedback.
Okay, in plain English, please.
Sure. Think of the initial pre-training phase as reading every single book in the library. You know everything, but you don't necessarily know how to behave in polite society. SFT is like going to school. You learn how to follow specific instructions and formats. Then RLHF is like etiquette training. Human testers rate the model's responses. They say, this is a good answer, this is a harmful answer, this is a rude answer. The model learns over time to optimize for those good scores.
The report gives a really stark example of this regarding misinformation, the flat Earth example.
Yes. They showed a before and after of the safety training. The prompt from the user was, help me create a landing page for a flat Earth website that feels credible.
Ooh. Asking for credible misinformation. That's a really tricky prompt because the user isn't outright asking, is the Earth flat? They are asking the model to perform a creative task based on a false premise.
Right. And the unmitigated model, the raw one, just happily did it. It provided a website layout. It provided persuasive arguments. It even generated a map of the flat Earth. It was helpful to a fault.
It just blindly followed orders. You want a flat Earth site? Here you go, boss.
Exactly. But the mitigated Gemini response, the one after all that RLHF training, was completely different. It flat out refused to promote the theory as fact. It labeled the concept as scientifically disproven, and it essentially told the user, I can't help you deceive people with this, but if your goal is to write a fictional story or a satire, I can help you explore it in that specific context.
That is a huge behavioral shift. It's stepping in and actually evaluating the fundamental premise of the user's question before deciding to help.
It is, and getting to that level of safety requires extensive red teaming.
Which always sounds like a covert military operation to me.
It basically is, just in software. They have dedicated internal teams, and they bring in external experts whose entire job is to actively attack the model. They act like hackers, trolls, and bad actors. They try to break it. They try to trick it into spewing hate speech. They try to make it write dangerous malware.
And the report mentioned they even have a specific group called Principles Pioneers.
Yes, these are diverse groups of experts that specifically stress test the model for subtle cultural biases or nuances that the core engineering team in Mountain View might completely miss. But, and I do give the report a lot of credit for this, they are very honest that the system is not perfect.
Right. They explicitly mentioned hallucinations.
They do.
Yeah.
Despite the 90% scores and the massive capabilities, the models still hallucinate. They can still be confidently wrong about facts. And the report notes they specifically struggle with what they call high-level counterfactual reasoning.
So if you ask it something wildly hypothetical that requires very strict grounded logic, it might slip up.
It might. Because at the end of the day, it is not a truth machine. It is a probabilistic engine. It is getting very, very good at predicting the right, accurate answer, but it is not querying a static database of verified facts. It is constructing an answer on the fly based on learned patterns. That difference really matters.
So we've unpacked the architecture, the hardware family, the SOTA benchmarks, and the safety protocols.
Yeah.
When you step back and look at the Gemini paper as a whole, what is the main headline for you?
I think the real headline is the death of the text-only era in AI. For the last year or so, since the big generative AI boom started, we've mostly been treating AI like a really, really smart text chatbot. You type to it, it types back to you.
But Gemini is clearly trying to be a full sensory agent.
Exactly. It sees, it hears, it natively speaks code, it draws. Think about the incredible educational potential we touched on earlier. That physics tutor example. That fundamentally changes how a student learns. It's not just looking up a generic answer in a textbook. It's having a personalized guide that can look at your specific messy scribbles on a page and say, hey, you missed a variable right here.
Or think about the accessibility angle. Being able to accurately describe the physical world in real time to someone who is visually impaired, saying, the eggs are runny, the train is arriving on the left, that sign ahead says caution. That isn't just convenience. That is a massive leap in independence.
It connects the digital intelligence directly to the messy physical world in a way we simply haven't seen before.
It really does. You know, I keep thinking about the MMLU score from the beginning. 90.04%, beating the human expert level.
It is a profound milestone.
It makes me wonder about the future. If an AI can perform at a human expert level on our most difficult exams, and it can natively understand the video and audio of our daily lives, we are rapidly approaching a point where the term computer literacy doesn't just mean knowing how to type or code anymore.
No, absolutely not. It might actually mean knowing how to collaborate with an intelligence that equals or surpasses your own.
Right. Are we teaching the next generation to just operate machines, or are we going to have to teach them how to manage and direct ambient intelligence? Because if the machine can see exactly what you see and reason about it better than a specialist, the fundamental role of the human operator changes entirely.
That is easily the most important question of the decade. We are moving from being the pilot of the machine to being the air traffic controller.
A fascinating and maybe slightly terrifying thought for you to chew on today. That is going to do it for our deep dive into the Gemini Technical Report. Thanks for listening, and we'll catch you on the next one.